Very good morning, students. So myself, Dr. Eustace Russell, working as assistant professor in the Department of Mechatronics Engineering at Sri Muthukumaran Institute of Technology. So far, we are covering. We have seen so far the subject called Engineering Mechanics of subject code ME25C02 under the regulation of 2025. The last lecture videos we have completed the polar movement of inertia, radius of gyration, and apart from this, some of the topics also we have covered in last three parts, that is 1, 2, and 3 of unit 3. Now we are under the last part of this unit 3. That is few topics we are going to concentrate in this unit 3. That is principal moment of inertia, product of inertia, and some of the including topic also we will see one by one. Now, product of inertia. The product of inertia of an area A is defined as Ixy is equal to integral of Ix dA. Ixy equal to 0 if the area A is symmetrical with respect to either or both coordinate axes. Now we can see one area we have took in that, and some of the measurement that is given over here, some coordinates, it is x dash and y dash and some angle. If the what is the area that is you are going to take, if it is symmetrical means then Ixy equal to 0. Then parallel axis theorem, we have already covered the parallel axis theorem. That is for a area we have seen. This is the product of inertia. Again we are going to write in terms of parallel axis theorem. That is parallel axis theorem for the products of inertia. How we are going to write means Ixy equal to I bar, what you are getting, Ix x dash y dash plus, then finally what you will get, x bar y bar a, then where I x dash y dash bar is the product of inertia of the area with respect to the centroidal axis x and y, which are parallel to x and y, axis, and x bar and y bar are the coordinates of this centroid of the area. The relations between the movements and the products of inertia in the primed and the unprimed coordinate system, that is assuming the coordinate axes are rotated counterclockwise through an angle theta. Now that is movement and inertia, it is primed and unprimed coordinate system, assuming the coordinate system of rotated anticlockwise. Anticlockwise means we have x from x to x dash, that is anticlockwise. Here we are, it is assumed an angle of theta with respect to x axis. It is moving in anti-clockwise direction, not in clockwise direction. Now the product of inertia, that is continuation of this one. Now upon derivation, we can write the product of inertia along x-axis, along y-axis, then xy axis also. Now we can see that formula, Ix plus Iy by 2 plus Ix minus Iy by 2 cos 2 theta minus Ixy sin 2 theta, then Iy dash is equal to Ix plus Iy by 2 minus Ix minus Iy by 2 cos 2 theta plus Ixy sin 2 theta. Then finally you will get Ix dash y dash is equal to Ix minus Iy by 2 sin 2 theta plus Ixy cos 2 theta. Then principal moment of inertia. How we are going to write means principal moment of inertia. Principal axis of the area about O are the two axes perpendicular to each other with respect to which the moments of inertia are maximum and minimum. The angle theta at which this occur are obtained as theta m, obtained from tan 2 theta m equal to minus 2 Ixy divided by Ix minus Iy. The corresponding maximum and minimum values of I are called principal moments of inertia of the area about O. They are given by I max, maximum and minimum. You will get the value Ix, we will have the expression Ix plus Iy by 2 plus or minus, inside the root you have to put square of Ix minus Iy by 2 the whole square plus Ixy the whole square. So these are the formulas you have to study for the principal moment of inertia. Now another one important topic, that is called moment of inertia of thin plates. Thin plates. So what you are going to see means one rectangle slab, that is thin plate, we are having the width, that is A, and the height depth of the plate is B, and the thickness of the plate is T. Now moment of inertia of the thin plates can be readily obtained from the moment of inertia of their areas. For rectangular plate, the moments of inertia are I a dash is equal to 1 by 12 m a square, I b b dash is equal to 1 by 12 m b square, then I c c dash is equal to nothing but I a dash plus I b b dash, which is also equal to 1 by 12 m a square plus b square. For a circular plate, they are for this plate, that is top one is the rectangular plate, the lower one we have given as a circular plate. Circular plate, the thickness is T and the radius of R. Now we have to use the formula IAA equal to IBB, IAA dash is equal to IBB dash is equal to 1 by 4 MR square. Then ICC is equal to, we have to add these two values, then finally you will get 1 2 will cut in the denominator, therefore you will get half MR square. So based on the formulas what I discussed in the previous, now we are going to see one basic problem in moment of inertia of thin plates. So now we are look on to the problem. Determine the mass moment of inertia of the thin plate about an axis perpendicular to the plate and passing through the point O. The material has a mass per unit area of 20 kilogram meter square. One circular hole, that is one square plate, that is a thin sheet. What you have done means 4 holes are drilled in this plate. You can see the dimension, all the dimensions are given clearly, that is 400 400. So in between the 2 holes, the horizontal as well as vertical also they have given 150 mm. In between the 2 holes it is given. Now we are going to see what are the basic process of this one. This body consists of consisted from 5 bodies, the plate and the 4 holes, one square plate. Then the mass moment of inertia about an axis passes through the point O. This means applying the parallel axis theorem. Already we have seen the parallel axis theorem. First of all, we have to see the mass of that plate. M, that is MP equal to 20 into A is equal to 20 into 0.4 into 0.4, which is equal to 3.2 kilogram. Then solid plate mass amount of inertia is equal to ICP equal to 1 by 12, that is 3.2 into 0.4 square plus 0.4 square. Then whole mass is equal to, you will get that is m height is equal to 20 into A. Again we are finding the whole mass, that is 20 into pi 0.05 the whole square, which is equal to 0.157 kg. Then holes mass moment of inertia ICH is equal to minus 4, that is 1 by 2 0.157 0.05 the whole square plus 0.157 0.15 the whole square. The total mass moment of inertia about the centroid, you will get IC is equal to ICP plus ICH is equal to 0.07 kg per meter square. So this is the total moment of inertia we have completed up to the mass moment of inertia. Now next thing we are going to find total mass moment of inertia about the point O using parallel axis theorem. Already we have seen with respect to area. Now we are seeing with respect to mass. Then what is the changes we have to take? The area will be replaced by the m, that is mass. IO equal to IC plus md square, where d is the distance between the centroid and the rotating point. Therefore the d is the 0.4 sine 45 degree we will get. Then finally you have to apply m is the mass, total mass of the system, which is equal to 3.6 minus 4 into 0.157 is equal to 2.572 kilogram. And finally, IO equal to, that is the first step. What is the formula we have discussed? Again, we have to apply here 0.07 plus 2.572.4 sine 45 the whole square, which is equal to 0.276 kg meter square. So these are the two references which I took for preparing this content. Kindly go through these references. So thank you, students. Thank you for your kind attention for listening these videos. We successfully completed unit 3 in with 4 parts. So kindly go through all the lecture videos. Please subscribe the channel. Please share this video to your friends. So we will meet in the upcoming video lecture. Thank you, students.